Hello, these are the video solutions for AP Physics C's suggested problem set 6.1. So we are starting with question 8.4, which has two vehicles approaching an intersection. So one of these is a 2,500 kilogram pickup traveling 14 meters per second from east to west. So I have a pickup, it is traveling from east to west, so it's going to the left, and it has an initial velocity in the x direction of negative 14 meters per second. Its mass, I'll call it mass P, is equal to 2,500 kilograms. And while I'm at it, I can go ahead and say V1, actually let's add a P to this. So I had V1x initially, we'll say V1px. And this will be V1py, so this is the initial velocity of the pickup truck in the y direction, is 0. We have a 1,500 kilogram sedan going from south to north, so it's moving upward. So here's my sedan. It has a mass of 1,500 kilograms, and it is moving northward at 23 meters per second. So this is going to be V1 sedan, so S, in the y direction, is positive 23 meters per second. So while I'm at it, I can go ahead and say that V1s in the x direction is 0. So part A says find the x and y components of the net momentum of this system. So what is the total momentum of this system? Let's change colors. So the total momentum of this system is going to be the momentum of the pickup truck and the momentum of the sedan added together. So since I'm looking for the x and y components, I will just find P total in the x, which would be the momentum of the pickup truck in the x plus the momentum of the sedan in the x, and P total in the y, which is going to be the same just for the y direction. So P pickup y plus P sedan y. So these aren't too difficult to actually put together. So I have P total in the x direction going to be mass of the pickup truck times V1 pickup truck in the x direction plus mass of the sedan times V1 of the sedan in the x direction. Now, the sedan has 0 initial velocity in the x direction, so it has 0 contribution to this. Therefore, my total in the x direction is just going to be 2,500 kilograms times negative 14 meters per second. And so my P total in the x direction is going to be, or my momentum total is going to be a rather large sounding negative 35,000 kilograms meters per second. So there is my x component of the total or net momentum. The y component will simply be the same setup, except my velocities will be in the y direction. So I have, mass of the pickup truck times V1 of the pickup truck in the y direction plus mass of the sedan times the velocity of the sedan in the y direction. So here, my pickup truck has 0 velocity in the y direction, and so it will have 0 contribution to the total momentum. So the total momentum of my system will end up being the mass of the sedan, so 1,500, times the initial velocity in the y direction for the sedan, which is 23. And so my total momentum for the y direction of this system will be 34,500 kilograms times meters per second. So those are the two components for the net momentum of this system. Now B simply asks, what are the magnitude and direction of the net momentum? So changing colors for B, all we need to do is add these together. So the magnitude and direction, so the magnitude of my momentum will simply be the square root of the x component squared plus the y component squared for the total momentum, all square rooted. So this is going to be the square root of So these are rather large numbers. So we have negative 35,000 squared plus 34,500 squared, all square rooted. So plugging this into your calculator, you'll find that the magnitude of this net momentum is 49,145. We'll just round it there. And that is kilograms times meters per second. So this is our magnitude. And we will find our direction from the arctangent of the vertical component, so momentum total in the y direction over momentum total in the x direction. And so that will be arctangent of, so make sure you include your signs here, 34,500 over negative 35,000. So if I go into my calculator and take the arctangent of this, I find my theta to be negative 44.6 degrees. And so I can leave it as just the negative 44.6, or you can translate this and say 44.6 degrees, and this is from our normal positive x direction, so from our positive x axis. So I can say 44.6 degrees south of east, according to my system of north, south, east, and west. For question 8.8, we have a baseball that has a mass of 0.145 kilograms. The velocity of the pitched ball, so we'll say here's my incoming pitched ball, is 45.0 meters per second. So let's say the pitcher is somewhere to the right and our pitched ball is heading this way. So our velocity before it's hit is negative 45 meters per second. And this is all in the x direction. So this right here is my before. After the bat hits the ball, my ball is now traveling in the opposite direction with 55 meters per second as its velocity. So the fact that these are opposite directions is rather important because part A asks us to find the magnitude of the change in momentum for the ball. So in order to find the change in momentum, which is equal to the impulse, I want to find P2 minus P1. So since this is all the x direction, I can write it as this and call it a day. So both of these will be equal to the mass of the ball times its final velocity minus the mass times its initial velocity. So for this ball, that will just be 0.145, and I'm going to factor out the m here and just look at the delta v. So I could say m times v2 minus v1. And that will be 0.145 kilograms times my final velocity, which is a positive 55 meters per second, minus my initial, which is a negative 45 meters per second. So we'll add another set of parentheses here. My change in momentum slash my impulse will be equal to 14.5 kilograms times meters per second. So this is our part A. Now part B says if the ball remains in contact with the bat for 2 milliseconds, find the magnitude of the average force applied by the bat. So how do we go about doing that? Well, from our knowledge of impulse, we know that impulse is equal to both change in momentum and an average force multiplied by some time interval. So technically all of these are vectors. And since I know the magnitude of my momentum change, I can simply solve this for an average force. So that would be equal to my change in momentum over my time interval. So really quickly, I'm going to convert my time interval to seconds because I have seconds over here. So delta t, which is equal to 2 milliseconds, would be converted to seconds just by saying there's 1 second per 1,000 milliseconds. So I'll have 0.002 seconds as my time interval. and my change in momentum is 14.5. So my average force will end up being of magnitude 7,250 newtons, acting on the ball over that short time interval. Question 8.11 is talking about a 2,150 kilogram rocket in outer space. So I'm going to go ahead and start by recording this mass. And it fires its engine that exerts a time-dependent force on it in the x direction. So this force is given as AT squared. And t is the time. So at t equals 1¼ seconds, the force has a magnitude of 781.25 newtons. So question A says, what is the value in SI units of this constant A? And we need to record those units. So this is actually not too terrible. So f of x at 1.25 will be equal to 781.25 newtons, and that is equal to A times 1.25 seconds squared. So rearranging all of this and just solving for A, algebraically you should find that A has a value of 500, and the units will work out to be newtons divided by seconds squared. So this is newtons per second. And remember, this is a constant, so it doesn't necessarily have a physical meaning by itself. Now, B asks, what impulse does the engine exert on the rocket during the 1½ second interval starting 2 seconds after the engine is fired? So let's interpret this really quick. So I want to find J but from a time of 2 seconds to a time of 1½ seconds later, which is 3 seconds. So we'll say this is T1 and this is T2. So how do I find the impulse? Well, first off, I have a force function here. So how does impulse relate to force? Well, impulse is change in momentum. Force, we know, is equal to, or net force rather, is equal to the rate of change of momentum with respect to time. So how do we get from this dp dt derivative to an actual change in momentum? Well, you guessed it. We have to integrate. So impulse is the integral of fx dt. Now, if this looks strange to you, that's because we just spent a lot of time with energy, where we were integrating force with respect to distance. So keep in mind, this is not with respect to distance. This is with respect to time. So for this particular problem, I'm going to use my force equation, which I found the value of A for, and I'm going to set up my limits of integration as 2 seconds to 3, I'm sorry, this should be 3.5. If you were curious about that, I just made a little mistake. So my impulse will be the integral from 2 seconds to 3.5 of 500 t squared dt. So I need to do this integral. So I'm going to first take the antiderivative of my 500 t squared. So I have 500 t, now I'm raising it up 1 power, so it goes to the third, and then I divide by that new power, which is 3. And then I'm evaluating this from 2 seconds to 3.5 seconds. So that translates to 500 thirds times my upper limit, which is 3.5, cubed minus 500 thirds times my lower limit, which is 2 cubed. And so the impulse here imparted by the engine will be 5,812, I'm not going to round this, 0.5. And my units will end up being kilograms times meters per second. Now, if you can't see why that is the case, so keep in mind my 500 is newtons per second squared, times, I'm getting time cubed here, so it's s cubed, And so this cancels out, and I end up with Newton seconds. So I could say Newton seconds, or I could simplify that to kilograms meters per second. So I'll go ahead and say Newton seconds, since we don't tend to see that very often. So this is the impulse imparted by my engine for that time interval. Now going back to C, it asks, by how much does the rocket's velocity change during this interval? And we have to assume that this is a constant mass. So we're actually going to make sure that that is the case here. We're not always going to have a constant mass, so we need to make sure we point that out. So my C will be, by how much does the rocket's velocity change? So I know that momentum and impulse are related as changes in momentum is equal to impulse. Now I can rewrite momentum change for a constant mass to be m times delta v. So what I'm looking for here is this delta v. So isolating delta v, I would have my impulse divided by my constant mass as my delta v. So this delta v will end up being the 5,812.5, I'll go ahead and write Newton seconds here, divided by the mass of the rocket, which we recorded as 2150 kilograms. And my delta v then for this time interval would be about 2.7, and then the units for this will end up being meters per second. And the reason for that would be, let's write out some units over here. We have newtons times seconds over kilograms. Well, a newton is a kilogram times a meter per second squared times seconds all over kilograms. So kilograms cancel, one of my seconds cancel, leaving me with just meters per second. So this is my delta v for that time interval. Question 8.13 utilizes a 2 kilogram stone. So I'm going to record that my stone has a mass of 2 kilograms first, and it is moving to the right on a frictionless surface at 5 meters per second. So I'll say V1 is 5 meters per second. And I'll see if that's positive because it's going to the right. So it's suddenly struck by an object that exerts a large horizontal force for a short period of time, and that is shown in this graph here. So we have a force of 2.5 kilonewtons that is acting for, it looks like, a 1 second interval. So first off is, what impulse is exerted by the force on this stone? So here I need to know that since impulse is equal to a force on average acting over a time interval, that would also be the area bounded in a force time plot or graph. So here that area would be represented in this rectangle. So what is that area in this case? Well, that area would be my force, which is 2.5 kilonewtons, times my time interval, which is 16 minus 15, and that's milliseconds. So we have a little weird bit of units going on here. So let's clean up the units. So 2.5 kilonewtons is 2,500 newtons. And this difference in time here is 1 millisecond, which is 1/1000th of a second. So my impulse in this case is actually just 2.5, and I can leave it as Newton seconds. So that's part A. Part B asks us, just after the force stops acting, find the magnitude and direction of the stone's velocity if it either acts to the right or to the left. So we'll do part 1, which is, let's say it's acting to the right. So my impulse, or my force rather, is acting to the right, which means F is positive. So what does that tell us? That means that our J is also positive. So we'll say J is, actually we'll say it's positive 2.5 Newton seconds. So our change in momentum is equal to this impulse. Since our initial momentum is known, we just need to set up our change in momentum as m times v2 minus m times v1. And what we're looking for is our velocity afterward. So I'm looking for v2. So v2 in this case will be equal to delta p, or our impulse, plus mv1 over our mass. So if the force acts to the right, our change in momentum is 2.5, I'll take the units out, 2.5 Newton seconds, plus our 2 kilograms times our initial velocity of 5 meters per second over our mass of 2 kilograms. So our final velocity for this case would be 6.25 meters per second. And then just to make sure there's no ambiguity in it, we'll say to the right. Now we can do the same thing for part II. This case, I'm moving to the left. So my force is going to be negative, which means that my impulse is going to be negative. So it's negative 2.5 Newton seconds. So I've already done this setup, so I'm going to just pull that over here. And I'll say that V2 is equal to my new delta P, or my new delta J, plus my initial momentum, which has not changed, over the mass. So my change in momentum in this case is now negative 2.5 Newton seconds, plus my 2 times 5 over my mass of 2. So in this case, my final velocity would be a smaller 3.75 meters per second. And I still get a positive value here. So it is still moving to the right. So don't be confused just because my force was acting to the left that I end up necessarily moving to the left after all of this has occurred. So question 8.16 is our first conservation of momentum question for this suggested problem set. We have an astronaut with a mass of 68.5 kilograms, and we have a tool that she is holding that has a mass of 2.25 kilograms. She throws the tool away from her with a speed of 3.2 meters per second relative to the space station. So firstly, we need to figure out if this is an initial or a final velocity. Well, she's doing the repair and then she throws the tool. So this 3.2 meters per second is actually going to be an after velocity. So what I can write is V1 for the tool is just equal to 0. Then she throws it, so it has some final velocity of 3.2 meters per second. Now, I'm just saying away from her seems to be positive. So the astronaut is holding the tool, and so she is also going to have an initial velocity that is 0. And then after she throws it, we don't know how far she's going or how fast she's moving, and we need to figure out which direction she's moving. So conservation of momentum set up here says that momentum before and momentum after will be equal. Well, momentum before must be 0. If I write it out, I have mass of the astronaut times her initial velocity plus mass of the tool times its initial velocity. Both of those are going to end up being 0 because they have 0 initial velocity. Afterward, the astronaut has some unknown velocity, while the tool has some velocity that is known to be 3.2 meters per second. So what I'm looking for is V2A. So I'm going to solve for this velocity, the final velocity of the astronaut, and see that it ends up being negative mass of the tool times its final velocity over the mass of the astronaut. So when I substitute in here, I have negative 2.25 kilograms times 3.2 meters per second over my mass of the astronaut, which is 68.5 kilograms. So how fast will this astronaut be moving? She'll be moving at 0.105 meters per second, and it will be a negative velocity. So what does that mean? That means she will be moving in the opposite direction of the tool. So this is the direction opposite the tool's motion. So this goes to the age-old situation where you're in space and the only way to go somewhere is to throw something away from you and hope you end up going in the right direction. So for question 8.18, we have two figure skaters with different weights. So I'll just draw these figure skaters as dots. or we can draw them as stick figures. And so they are together. So we have figure skater A and figure skater B. So the weight of figure skater A is 625 newtons. The weight of figure skater B is 725 newtons. Now, I don't necessarily care about their weights. So something that I know I'm going to need to do right away is move this around and find the mass of each of these figure skaters. The reason why is mass dictates changes in momentum. So I'm going to go ahead and say, or remind you, that weight is equal to mg. So the mass of each of these would be weight divided by our gravitational field strength. So the mass of figure skater A is going to be 625 divided by, we'll go ahead and just use 10 here. So the mass of A will end up being 62.5 kilograms. And the mass of B will be the 725 divided by 10. So the mass of B will be 72.5 kilograms. Now, these two figure skaters are standing together, and they push off of each other on frictionless ice. So after they push off of each other, they will be moving in opposite directions. So I have one figure skater going to, doesn't matter which one, moving, so the heavier skater moves at 1.5 meters per second. So we'll say this is V2B is 1.5 meters per second. We want to know how fast the lighter figure skater will be moving. So this will be V2 for A. We don't know how fast she'll be moving, but she will be going the other way. So this screams conservation of momentum. So conservation momentum setup for this will be, let's go, here we go. So conservation of momentum will be P1 equals P2. And so for this, my initial momentum will be 0. I'm going to go ahead and start simplifying it before I do anything else. So they're just together, then they push off. So 0 will be equal to the mass of A times the final velocity of A plus the mass of B times the final velocity of B. So the final velocity of A must be equal to negative mass of B times B's final velocity over the mass of A. So this will be negative, so the mass of B is the 72.5 kilograms, make sure you're using the correct mass, times the 1.5 meters per second they'll be traveling, over the 62.5 kilograms for the lighter figure skater. So the lighter figure skater's velocity will be a negative 1.74 meters per second. So she will be moving, or they will be moving, in the opposite direction at a slightly faster speed. Now B says how much energy or kinetic energy is created during the skater's maneuver, and where does this energy come from? So in order to look at this, I'm going to take a quick look and say, all right, delta K in this case is going to be K2 minus K1. So this is my kinetic energy. So that'll be 1/2 the mass of A times V2A squared plus 1/2 the mass of B times V2B squared. And that's going to be it, right? It's going to be minus 0 because there is no initial velocity, so the initial kinetic energy is 0. So now I can say, all right, the change in kinetic energy that is created, or the kinetic energy that's created here, is just going to be 1/2 62.5 times the negative 1.74 that I just found squared plus 1/2 the 72.5 times the 1.5 that I was given squared. My change in kinetic energy then works out to be 176, we'll go ahead and just put the whole number here, 0.175 joules. So this is the kinetic energy that appears to come out of nowhere. So where did this come from? Well, it came from some chemical energy that was released by the figure skaters' bodies. So you can trace it back as far as you want depending on your biology knowledge. But it was essentially released as ATP, goes through the muscles, and that is translated to a force. So that is where this kinetic energy seems to have just appeared from. Question 8.21. On a frictionless table, puck A is moving toward puck B that is initially at rest. So here's puck A, and it is moving toward puck B that is initially at rest. So I'm going to go ahead and label this as mass with A of 0.25 kilograms, and is moving toward a mass B of 0.35 kilograms. And puck A has puck B rather has an initial velocity. So actually we'll do this. We'll say initial velocity. So V1B in the X is 0, and V1B in the Y is 0. Now we don't know anything about the initial velocity of A. So I'm going to go ahead and write that. So V1A in the X, don't know. V1A in the Y, don't know. So this is all my before. After the collision, puck A has a velocity of 0.120 meters per second to the left. So here's my A after the collision. And same mass, but now it has an x velocity, so this is V2A in the x, of negative 0.12 meters per second, and no mention of the y, so we'll assume that it's 0. And puck B, so this is A, this is B, is moving at 0.65 meters per second to the right, so it's positive 0.65 meters per second. Again, no mention of the y, so we'll assume that that is 0. So A asks, what is the speed of puck A before the collision? So we're reverse engineering our velocity, and it really doesn't matter which one is the before and which is the after. So we'll start, there's a collision occurring, so we'll start by saying that momentum is conserved. So P1 equals P2, and we could also go ahead and just say P1x equals P2x. So this translates to MA V1AX plus MB times V1BX is equal to MA times V2A in the x plus MB times V2B in the x. So my velocities of B are 0 initially, so I can get rid of that term. And then I'm looking for V1AX. So if I solve for V1AX in this case, I will have MA V2AX plus MB V2BX all over MA. So V1A in the x direction, we can substitute in our values, and we'll have 0.25 times negative 0.12 plus 0.35 times positive 0.65 all over 0.25. So solving for this in our calculator, we find that our velocity for the A puck initially was, was 0.79 meters per second. And that was to the right. Now part B says, calculate the change in total kinetic energy of the system that occurs. So for part B, we're calculating the change in total kinetic energy of the system that occurs during this collision. So my change in kinetic energy will just be initial kinetic energy final minus initial kinetic energy. So my final kinetic energy will be 1/2 mass A times V2A squared plus 1/2 mass B times V2B squared minus my initial kinetic energy, which only hinges on mass A. So that's 1/2 mass A times V1A squared. So my change in kinetic energy then will be, I can't factor anything out really, so I have 1/2 times, so my mass A will be 0.25 times V2A, which is negative 0.12 squared, plus mass B, which is 0.35 times V2B, which is 0.65 squared, minus mass A, which is 0.25 again, times V1A, which we just found to be 0.79 squared. I'm totally out of room, but you get the point. So my change in kinetic energy then we just calculate to be a very tiny negative 0.002275 joules. So this is a very small change in kinetic energy, but it is negative. That means that kinetic energy is leaving our system, which makes sense because there's some deformation going on here. So even though this may be a nearly elastic collision, some amount of kinetic energy is still going toward deforming these pucks.